Now, and let me warn you beforehand. This is number theory all over again. So this is again some math, but please don't be afraid, because the thing is, I think this is the last math part. But you need all this for cryptography, just like you needed Galois fields for doing AES. So this we'll see in a minute that we need that. So this, most of the public key cryptography that we will learn later on, which we haven't done yet, depends upon prime numbers. Very large prime numbers. Depends upon the fact that you cannot factor easily very large prime numbers. If you can factor the prime numbers, large prime numbers, you can basically, so the whole certificates, etc., that you get from, you can get a certificate, those certificates are all based upon public key. Okay? And they're all based upon the difficulty in prime numbers. So I'm going to tell you all about primes today. Okay? And so there are several things that are well known for prime numbers. And it's a whole series of theorems we'll go through. So Fermat's little theorem. It says that if P is prime, then for all integers, a raised to P minus 1 is 1. If P is prime, then for all integers, a raised to P minus 1 is just 1 mod P. So let's see. 5 is a prime. Right? If 5 is a prime, then 1 raised to 4, P minus 1. If you do mod, how much does it come out? 1 mod 5 is 1. So that's given. What about 2 raised to 4 mod 5? How much is 2 raised to 4? Anybody? 16. 16 mod 5 is 1. 3 raised to 4 mod 5. How much is 3 raised to 4? 81 mod 5 is 1. And 4 raised to 4 mod 5. 4 raised to 4. 16 times 16, 256. Mod 5 is 1. So this is true for all numbers and all primes. Okay? That's the Fermat theorem. Now, I think it's called Euler's quotient function. So anyway, so Euler's quotient function is a number psi n, this phi n, such that if you take let me define complete set of residues. If you take a number n, if you take any number n, it doesn't have to be prime. If you take any number of n, complete set of residues, which means that if you divide any number by n, the remainder that you will get would be 0 through n minus 1. Right? That is called complete set of residues. 0 through n minus 1. But if you take only those residues which are relatively prime to n, then that is called reduced set of residues. For example, complete set of residues for 10 is 0 to 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is what you will get if your n was 10. However, if you just cross out things which are not relatively prime to 10, so 2 is not relatively prime because they have a greatest common divisor which is other than 1. So therefore 2 is not, 4 is not, 6 is not, and 8. So you cross out those, what you get, and 0 is basically 10, so that is crossed out as well. So what you get is 1, 3, 7, 9. This is the reduced set. So these numbers are relatively prime to n. Okay, because 1, 3, 7, 9 have no common factors with 10. Now, so this guy figured it out that the total number of such numbers is phi n, and it is equal to p minus 1 for prime numbers And if it is not prime, then it is equal to p minus 1 times q minus 1 times whatever the factors, prime factors are. Okay, so let's take an example. 37 is prime. So its complete set will have 0 to 37 numbers, and the reduced set will have 36. Basically 0 will get out, but basically everything else is there. Right, p minus 1. But take a number 21. 21 is not prime. So 21 is 3 times 7, p times q. So you take 3 minus 1 and 7 minus 1, and you get 2 times 6, 12. So there are 12 numbers. You can write down all the numbers which are, so it's very easy to do. How do you calculate this? You just write down numbers 0 to 20, and then cross out the numbers which are not relatively prime, which means not relatively, basically, so everything that is multiple of 3 you cross out, and everything that is multiple of 7 you cross out the 0. The remaining you will have 12 numbers which are in the reduced set. Can you do that? I mean, can everybody calculate at least by empirically, and then you don't have to do it empirically after you know this theorem or this function. You can do it without actually expanding out the whole thing and computing. But you understand what we are counting here. What we are counting here is all the numbers which are less than n, between 0 and n minus 1, that are relatively prime to n, that have no common factors with n. Okay? In case of prime numbers, that number is p minus 1. In case of non-prime numbers, you have to find out the factors and then just write down the primes and you will get that number. Okay? Now, then here is a theorem which says that a raised to phi n equal to 1. So Fermat said that a raised to p minus 1 is 1, right? A raised to p minus 1, which where p is the prime number. Now this theorem applies to non-prime numbers. If n is prime, then this will become a raised to p minus 1 mod 1 equal to 1, right? So that will become Fermat theorem. But this is more general because now if n is not prime, then also we know what will make it 1. Okay? So here's an example. Let's say n equal to 10. Then we found out a n equal to 10, phi n is 4. We already know that. Right? So everything raised to 4 will be 1. So now you can do 1 raised to 4, 2 raised to 4, 3 raised to 4, 5 raised to 4, mod 10 would be 1. Oh, only for those, by the way, oh sorry, I missed one key point. Only for those a's which are relatively prime to n. So you cannot take 2 raised to 4. Sorry. You have to have only these numbers. 1, 3, 7, 9. Those are relatively prime. So 1 raised to 4, 3 raised to 4, 7 raised to 4, and 9 raised to 4, mod 10 will be 1 by this theorem. Okay? And so basically those numbers which are not relative prime, which are not in the reduced set, they will not be 1, and this will be 1, right? And now here, similar, there is another example here. Here I am taking an example of 11. Now 11 is a prime number, so we can go back to the previous theorem, which is Fermat theorem, which says for everything raised to 10, mod 11 would be 1, right? So that's not for prime. That is basically Fermat theorem. If n is prime, then you go back to the Fermat theorem. If n is not prime, then this guy extended it further. Now, another way to write this thing is that a raised to phi n is 1, but a raised to phi n plus 1 is a, back to a. I mean, you multiply both sides by a, you get a. So, same thing for Fermat's theorem. A raised to p minus 1 is 1, a raised to p is a. Now, if you know these theorems, then I can ask you in the exam next week, what is this value? You don't have to calculate. If I ask you, what is 2 raised to 13 raised to 2 raised to 15, whatever that is, you should be able to say it is 1. Right? If the numbers are right. Can you do that? Right? And so if you did the calculation, that would be wrong. You have to just know the theorem. All right. Now, next thing. Michael Rabin algorithm for primality. So last week, by the way, this conference which I went to last week, I met this guy. Actually, he was given an award there, KSA. His claim to fame is that he invented an algorithm for primality, which is the shortest algorithm. He wrote an 11-line code. You can find out whether the number is a prime or not. So it competes with Miller-Rabin. Because the book even talked about his name, Agrawala and something like that. So his name, and then said that algorithm is shortest, but this is most efficient. Efficient means less time it will take to execute on a computer. Their algorithm is deterministic, this is probabilistic. So with this one, you can do, in certain number of trials, and you can be almost pretty sure, but not ever sure, fully sure, that this is prime or not. With that algorithm, Agrawala's algorithm, his name was Mahindra something, I forget the last name. So, Mahindra something. So this is a difficult thing. I mean, this is something that, you get Nobel Prize for, okay? So this is how you test. If you want to test something for primality, this is how you start by this algorithm. By this algorithm, you, and this is based upon the Fermat theorem, you take a number k and q such that the number n that you want to try out is n minus 1 is equal to 2 raised to k comma q. Alright? So you find k and q such that n minus 1 is equal to 2 raised to k times q. Now how do you find k and q given a number n? Well, if number n is even, obviously it is not a prime. Right? It doesn't matter what the digits before are. If the last digit is an even number, you know that this is not a prime. So the last digit has to be an odd number. If you subtract 1, the rest would be even number. Right? So n minus 1 is a even number. So you divide it by 2. If you still get an even number, you divide by 2 again, you divide by 2 again until you get an odd number. And that is your q. Alright? So given any number, you can find out 2 raised to k times q. You can find out k and q. Feel okay? Right? So n minus 1 has to be 2 raised to k minus q. K times q. Alright. So select an integer a. Now you randomly select an integer a. This is where the randomness comes in. You can never be sure. So you select a number a between 0 and n minus 1. And a raised to q mod n, if a raised to q mod n is 1, then you say inconclusive. Then you say, I don't know whether this is prime or not. Okay? And you stop right there. Sorry, I don't know. So this is the weakness of this algorithm. It doesn't tell you that, yeah, this is not or this is it, right? It might say, I don't know. Then, for j equal to 0 to k minus 1, all you do is you keep squaring that number a. So a raised to jq, a raised to 2 raised to jq mod n. If that is equal to n minus 1, then you return inconclusive. And if nothing happens here, then you say it is composite. Okay? So all right. So let's see. This looks like a little bit complicated formula: a raised to 2 raised to j raised to q and all that. But in the next slide, I have an example where you'll see this is all squaring. So keep squaring a until you say either it is inconclusive or composite.